A warm welcome to all the attendees. I'm Mahima and
And I'm Meghna.
BMS AI interns of Cellstrat. Heart diseases are the major cause for human mortality rate. Correct diagnosis and treatment at an early stage will save people from heart disease and will decrease mortality rate due to heart problems. Today, we are going to present our understanding of various risk factors which cause heart diseases and a solution for predicting heart disease. So here, prediction algorithms are trained with a known data set to arrive at a classifier, which then predicts the diseases for unknown data with the help of classifying attributes. These attributes can also be called as features or parameters or the risk factors, which play a vital role in causing heart disease in the first place. This is the flow of our webinar. So I will be constantly swapping my screens between this PPT and the code in the Jupyter notebook. So starting off with importing essential libraries.
Uh, we first start
Yeah,
off by importing the essential libraries such as NumPy, Pandas, Matplotlib, and Seaborn. We also use scikit-learn and TensorFlow for the later models, which will be imported as and when the models arrive.
now let's take a deep dive into our data set. These are all called the classifying attributes. So we have around 13 classifying attributes. Starting off with age. Uh, the minimum age of men around which the heart diseases will start is 45, and the woman age is 55 years. Then comes the sex, that is the gender. So here in our model, we have considered 0 to be as female and 1 to be male. Next is the chest pain type. There are various types of chest pain. The chest pain is also commonly known as angina. 1, 2, 3, 4 represent typical angina, atypical angina, non-angina pain, and asymptomatic. Then comes resting BP. These are the parameters. Uh, these are the parameters for the resting BP. Then comes the cholesterol. Cholesterol is nothing but the serum cholesterol. Cholesterol is a waxy fat-like substance that is found in all the cells of your body. And then fasting blood sugar. Fasting blood sugar is basically obtained by a test called as fasting blood glucose or fasting blood sugar. This basically determines the glucose in your blood sample after an overnight fast, hence known as fasting. Then resting ECG result. The resting ECG result can detect certain heart conditions like myocardial infarction, cardiac infraction, etc. Thalach, that is maximum heart rate achieved, is either 0 or 1. Exercise induced angina, sorry. This is also known as the stable angina, which is usually triggered by physical activity, like when you climb stairs, exercise or walk, etc. Next, the attributes 10, 11, basically we can see them in the ECG. That is the electrocardiograph. So, which is represented by PQRST. So, old peak ST, the depression induced by excessive relative to rest. Let me just draw it for you and explain you how it actually looks. For the normal person, the ECG should be somewhat similar to this. You can see the shift in the curve over here. This is mainly that is mainly due to the ST depression. Next comes the slope of the peak exercise ST segment. Then the number of major vessels, and then the thallium stress test. The thallium stress test. The thallium stress test. Basically, it is used to detect the inherent. Uh, sorry. A thallium stress test is a nuclear imaging test that shows how well blood flows into your heart while you're exercising or when you're at rest. This test is also known as cardiac or nuclear stress test. Then comes the target, which is basically to detect whether the heart disease is present or not, that is 0 or 1. Here in the code, you can see that initially we have imported a file called heart.csv where our dataset is present. And then here the dataset is represented in the columns and you can see the attributes age, sex, CP, cholesterol, FPS, etc. And then this is the explanation that I have given you right now. And now here in the dataset, we can observe that the target values are usually zeros or ones. Hence, we are considering this to be a classification problem with target variable having 0 and 1. And we can also check the correlation between the columns. The correlation is nothing but it is used to determine the top 6 to 8 or the best attributes which we can use to predict heart disease. Now, Meghna is going to explain you about exploratory data analysis.
Exploratory data analysis, we first analyze the target variable. We can see that we have 303 values in our data set, out of which 165 of them have heart disease and 138 do not have heart disease. Here we've later down we've calculated the percentage without heart problems and percentage with heart problems. Next comes the sex feature. We've plotted a bar graph between the sex and the target. We can observe that females are more likely to have heart problems than males. Now coming to analyzing the chest pain feature. Once we plot the bar graph similar to the above, we can find that chest pain with type 0 with who have typical angina are less likely to have heart problems than the others. Next, we analyze the fasting blood sugar feature. We do the same thing as above, and there's no much difference because, as you can see, they're almost close to each other, around 0.5.
Yeah, maybe you can scroll a little bit slowly. There's a comment which came.
Oh, yes, sir.
Now, Mahima will be analyzing the uh, rest ECG feature.
The resting electrocardiography results are as follows over here. You can see uh, 0, 1, and 2. You can observe that the one feature over here has gone too high. So this says that we realize that people with resting electrocardiography results with 1 are most likely to have heart disease than 2, 1 and 0, 1 being the highest. And next coming the exang feature, that is exercise induced angina. Here we can clearly observe that 0 has reached its peak compared to 1. So people with having a 0 exang feature will have are more likely to have heart disease than 1.
The slope feature, though it is not one of the major features, we can observe that the slope, the people who have the slope feature as 2 have much are much more likely to have heart pain than people with slope 0 or slope 1. Next, we analyze the CA feature, which is the and we can realize that next Mahima will be explaining about the test and train split.
Now it's time to split the data. Take the data frame and split it into two groups, a training set and then a test set. Here we use 80-20 ratio. So 80% of the data will go into training set and 20% will go into test set. Of course, it's not necessary that we always take the same ratio, but we have considered this ratio to be perfect for our model. Now we'll be explaining about the model fitting in detail. First, first moving on to logistic regression. So basically, what we are going to explain over here is the different classifiers that we have used to predict the heart disease. And finally, we are going to conclude which classifier will give us the highest accuracy for heart disease prediction. Firstly, I'm going to speak about logistic regression classifier. Logistic regression predicts if something will happen or not happen. Logistic regression is used when a response variable has only two outcomes, yes or no, true or false. We refer to logistic regression as a binary classifier. Since there are only two outcomes, let's just try to understand this with a very simple example. Let's say that you have a startup company and you are trying to figure out whether the startup will be profitable or not. That's binary classification. Basically, having profit or non profitable as the two possible outcomes. So, let's use the initial funding to be the independent variable. This graph, which is shown here in the top, where the x-axis is funding and the y-axis is the profit, they're showing you the linear regression basically. Now I'm going to compare between linear regression and logistic regression so that you get a better understanding of the logistic regression, and then I'm going to take you back to the code and make you correlate the concepts for a better understanding. Here we can see in the first graph that this is not, uh, so basically over here they're just predicting that as the funding increases, the startup will have more profit. And this is not binary classification. So if you want to predict how much profit will be made, then you're going to use linear regression. Else, if you have to predict uh, only the two cases, that is profitable or non-profitable, then you're going to use uh, logistic regression. Now, in this next graph, the x-axis is our independent variable, that is funding, and the y-axis is no longer a dependent variable, that is profit, but rather the probability of profit. For logistic regression, you will make use of a sigmoid function. The sigmoid curve is the line of the best fit. In this example, we have plotted several companies with various funding levels from 10 to 70 and indicated whether they are 0, that is non-profitable, or 1, profitable on the graph. In this example, given the amount of funding, we can calculate the probability the company will be profitable or not profitable. If you use a threshold line of 0.5 as shown in the figure, then you can have that as your best classifier. If the probability is 0.5 or higher, the company is profitable. If the probability is lower than 0.5, then it is non-profitable. Now here in the code, we have done exactly the same manner. All the parameters, the 13 parameters which we previously saw, that is the classification attributes, we have used those to classify between a person suffering from heart disease and a person who is not suffering from a heart disease. And based on that, we have chosen a particular classifier, that is logistic regression classifier. And then here, when we run this code of logistic regression, we can see that 85.25% of accuracy is being obtained from this model. Now Meghna is going to
Coming
explain you about naive Bayes.
naive Bayes, it's a classification technique based on the Bayes theorem, with an assumption that all the predictors are independent to each other. In simple terms, naive Bayes classifier assumes the presence of a particular feature in a class which is unrelated to the presence of any other feature. Here in our code, we are using a Gaussian naive Bayes uh, model, which would be much simpler for a large data set and also more accurate. Uh, The formula for the Bayes theorem is given here. Uh, so basically what we do is we take the mean and standard deviation of all the individual parameters and plot the Gaussian distribution, which looks like the figure 2. So there would be 13 Gaussian graphs, and each of the graphs will have 2 Gaussian curves, each representing one of the classes, that is the blue representing the presence of heart disease and the red representing the absence of heart disease. We calculate the prior probabilities, which is P of C over here in this formula. The prior probability is calculated whether the person has a disease or not based on the training data set. When a new individual gives the parameters, that is when he goes for a test and the parameters come out, we calculate the probability that the person, we initially assume that the person has a heart disease and then calculate the probability that the person has a heart disease. So that is calculated by the probability of the prior probability of the person having the heart disease multiplied by the likelihood of each of the parameter given that they do not have the disease. Note that over here the likelihood is the y-axis on the curve that corresponds to the x-axis. The log of the function is taken to prevent the underflow, and the probability is compared with the final report. Thus, what we do is we take the prior probability as that the person has heart disease, and then we take the prior probability that the person does not have heart disease, and we calculate the probability of the person having the heart disease or not. We compare those two and then give the result of which has higher probability. The cons of this naive Bayes model is that in the test data set, if the categorical variable has a category which was not observed in the training data set, the model will assign 0 probability and will be unable to make the prediction. This is called a zero frequency. The smoothing technique called Laplace estimation is used to avoid this. We have done the same thing in the code, and we have calculated the accuracy of the naive Bayes model, which turned out to be 85.25%.
SVM, the support vector machine. This is the type of classification algorithm that classifies data based on its features. An SVM will classify any new element into one of the classes. This example is, now we are going to take an example. This example is to classify cricket players into batsmen or bowlers using runs to wicket ratio. The x-axis over here in all the graphs is wickets, and the y-axis represents the runs. The bats in the figure represent the batsmen, and the balls in the figure represent the bowlers. Now, a player with more runs would be obviously be considered as a batsman, and the player with more wickets would be considered a bowler. Now, when we plot the data, we can see a clear separation between the class of batsmen and bowlers. Now, we want to classify player variable, the player variable, that is the unknown value, which is now entered uh, into the picture as a batsman or a bowler. A decision boundary is now required in order to classify the new unknown variable. The decision boundary is nothing but the separation between the two classes. Now you can see the green, blue, and the yellow lines that are drawn between in order to separate the two classes. We cannot classify the unknown player into its correct class using multiple separating lines. Hence, we need to choose one best separating line for the data set. The best line is selected by computing the maximum margin from equidistant support vectors. Now, in the image that is present, the rest of the four images, we can see the bats and the balls on the both the sides, which are being highlighted. So these are considered to be the support vectors. The support vectors are nothing but the points which are very close to the dividing line. That is the blue, the yellow, or the green line, which you can see in the center. Using the support vectors, we can select the best lines to divide the data. Now, as we dive deep into the pictures, we can observe that the taking the first image, that is the yellow line, where the yellow line is highlighted, we can see that one of the bat is very close to the main line. To the main line. So we can say that this is not our hyperplane. The main line in the between is called as a hyperplane. So basically, in order to choose a hyperplane, we have to keep certain things in our mind. That is, the support vectors must have maximum distance from the hyperplane. This can be observed in the last diagram, wherein the green line is present. But whereas the first two images, where the yellow line and the blue line are present, we can see that the bat and the ball are either close or far away, but not at the maximum distance from the hyperplane. So this can also be calculated mathematically. Here we can observe the center line is called as the hyperplane, and you can see where the positive hyperplane is pointed out, and then the negative hyperplane is pointed out. And the maximum margin is the total distance that is present between the positive hyperplane and the negative hyperplane. The center hyperplane is also known as maximum margin hyperplane. And you can also clearly see the pointed out support vectors. Now, basically from this, we can understand that we can divide the people having heart disease and people not having heart disease into two different classes by a classifier, that is hyperplane in between. So our goal is to choose an appropriate hyperplane. So we have done the same thing in this code over here by taking into consideration all the parameters, and then when we run this code, we get an accuracy of about 81.97%.
Now I'll be explaining about the k nearest neighbors, also called as KNN for short. It is one of the most popular machine learning algorithm used for classification problems. Consider the figure given here, the figure 1 in this. Here, the star represents one of the class, that is class A, and the triangles represent class B. When a new example data is given to classify for us, and which is present in the middle, that is shown as the question mark, the yellow one, what we initially do is we initially set the k value to a number. There is no ultimate method to determine the optimum k value. I'll be talking about the how to set the k parameter later. We initially set the k value. For getting the predicted class, we iterate from 1 to total number of training data points. Then we calculate the distance between the test dataset and each row of the training dataset. And most common distance metric, that is the Euclidean distance measure, is used to calculate the distance. The calculated distances are arranged in ascending order based on the distance. And then the top k rows from whatever the k value we've set, we take those many nearest values, and the most frequent class of it is taken, and the class is predicted. Similar, this graph, the linear graph is for variables of two types. I mean, if the parameters are only two, in case the parameters are more, we use a heat map to show it, and the procedure followed is the same. There are ways to increase the accuracy of the k nearest neighbors. We conduct the chi-squared attribute evaluation to determine which variables are most important than the others to attain more accuracy. So the KNN weighting experiments will give top 6 variables. The top 6 variables are given as weight 2, while the other 7 are given weight 1. Then we do the KNN weighting experiment to check the accuracy. One of the most common ways to select the k parameter is taking the square root of the training data set and checking the accuracy. The advantages and disadvantages of taking the k value plays an important role. If the k value is taken low, there will be it can be noisy and subject to the effect of outliers. Large values of k will give a smooth curve over things, but the k shouldn't be so large that the category with only one of the few samples in it will always be outvoted by the other categories. Here in the code, Mahima, the code. Yeah. In the code, we have taken all the parameters into consideration and iterated and found the ideal k value to be 7. Since it's binary classification and the target value has either 1 or 2, either 0 or 1, that is only 2 values, we tend to take the k value to be an odd number. And we found that k value is equal to 7 will give the maximum accuracy, which is 67.21%. Now Mahima will be explaining. Oh no, I'll be doing it, I guess. Uh, Next slide. Yeah. Uh, the next model we are going to use is the decision tree model. Uh, the next slide, please. Yeah. The decision tree model is a supervised machine learning algorithm that can be used for both classification and regression problems. Here we're going to use it for classification. A decision tree is, is simply a series of sequential decisions made to reach a specific result. As we can see over here, to identify which animal it is among the group of animals, we set the color. In the group of animals, we first ask the question if the color is yellow. If the color is yellow and it's true, then we can find that uh, tigers and giraffes fall under this category. If it is false, then it will be monkeys and elephants. Then we ask the question whether the height is less than 10 or equal to 10 or greater than 10. Uh, if the height is equal to 10, uh, which turns out to be true in the second decision node, if it is true, it turns out to be giraffe, and if it's false, it turns out to be tigers. The same thing is done even for the right subtree. Uh, if the height is less than 10, it's a monkey, and if it's not, it'll be an elephant. Uh, the basic idea is uh, the top, uh, the initial question we ask, that is called the root node. And uh, once you split it, the second question we ask would be the decision node. The decision node further might lead to another decision node, or it might lead to a terminal node, which is also called as the leaf node. The decision node along with the terminal nodes, that is the last decision node, is called a branch or a subtree. Uh, the most important terminologies used are entropy, information gain, and Gini index. Entropy is the measure of uncertainty or randomness in the data set. Entropy handles how the decision tree splits the data. Information gain. Information gain measures the decrease in entropy after the data set is split. Gini index is the uh, most important feature that will be used. The Gini index is used to determine the correct variable for splitting the nodes. It measures how often a randomly chosen variable would be incorrectly identified. So uh, the Gini impurity for a parameter is the weighted average of Gini impurities for the leaf nodes. We do it for all the parameters, and the parameter with the least Gini impurity becomes the uh, top of the will become the root node. We repeat the same process by calculating the Gini index and comparing it to the least. If it is least, it becomes the next decision node, uh, and goes on. Uh, some of the steps involved, these are the steps involved in forming a decision tree. We calculate the Gini impurity score. If the node has the lowest score, we do not split or separate the patients anymore, and it becomes a leaf node. If separating the data results in improvement, then we pick a separation with lowest impurity value. Uh, there is another feature better than decision tree, which is called the random forest. Mahima will be explaining about it. Oh, we found the accuracy of the decision tree to be 81% after running the code and predicting it. In the code, uh, in the code, uh, we set the maximum accuracy to 0 initially. Then we train the data and try different decision trees. Once we get each time we get an accuracy, we compare it with the maximum accuracy. If the maximum accuracy is uh, if the current accuracy is greater than the maximum accuracy, then the maximum accuracy is the current accuracy, and we found it to be 81.97%. Now Mahima will be explaining about the random forest.
Random forest is a learning method that operates by constructing multiple decision trees. The final decision is made based on majority of trees and is chosen by the random forest. Now, to understand how this works, let's just take an example. Let's just say that we want to classify the different types of fruits in the bowl based on various features such as the fruit colors, the diameters, the specific labels like uh, apples, grapes, into its specific labels. Now, here we can see that the instance is nothing but the fruit bowl that we have considered, and then there are various different trees that are being created. Now, the first step to do is what we have to do is to create a bootstrapped dataset. A bootstrap dataset is nothing but the dataset which is randomly got from the original dataset. Basically, you'll be filling in you'll be filling in the data that you will get from the original dataset randomly. And next, you will have to create a decision tree, just like you have created over here the tree 1, tree 2, and tree n. These are the three decision trees that you'll be creating. But there is a different approach over here. You are going to use a random subset at each step. And then again, you're going to go back to the step A, and again, you're going to repeat it so that you get n number of trees like this. Now, in this example, the fruits, the first the all the characters which are based, which are all the characters which are present in the tree 1, tree 2, and tree 3 by the subsets are gonna check in details of the fruit that is being picked. Now, after running through all the decision trees, the tree 1 says that its output is an apple, and tree 2 says its output is an apple, and tree n says that its output is a banana. So now we can observe that the majority voting over here obtained is apple. So hence the final product is going to be an apple again. Similarly, over here in this code, what we have to do is once we input the entire data set, and then once the decision trees are formed from the bootstrap data set, then after the randomly picked person after the randomly picked person undergoes the various decision trees, and then the output you get, and then once you get the output, and then once you go to the majority voting, and then if the majority voting says that the person is being detected with a heart disease, then that's going to be our final output, saying that the person has heart disease, else the other way, the vice versa. So using this random forest method of classifier, we can see that we have achieved of about 95.08 percentage of accuracy. Now Meghna is gonna explain you about the XGBoost classifier.
Okay, so XGBoost stands for Extreme Gradient Boosting. It is an advanced implementation of the gradient boosting algorithm. Uh, in our code, most of the parameters used in XGBoost are taken to default value. Uh, the parameters which are taken to default are given over here. Uh, the advantages of XGBoost uh, are many. Some of them are unlike gradient boosting model, that is GBM. Uh, XGBoost has regularization, which prevents overfitting. Thus, it's also called as regularized boosting. Uh, XGBoost has a feature of tree pruning. It splits the data up to maximum depth, and pruning occurs in backward process. XGBoost, one of the major advantages of XGBoost is that it is pre-trained to handle missing values in the data set. It also has a built-in cross-validation. Uh, uh, Back to the code. Uh, the code. Mahima, the code. Yeah, here in the code, we have used one of the parameter called as objective equal to binary logistic. Uh, the uh, objective stands for uh, defining how the loss function is minimized. Uh, The loss function is minimized by using logistic regression for binary classification, and it returns the predicted probability and not the class. It says the probability and does not exactly tell whether the person is suffering from heart disease or not. It just predicts the probability. Uh, we calculated the accuracy of the XGBoost model and found that it was 85.25%. Next is the neural network, uh, which Mahima will be explaining.
So you are
So
showing the same
we can also,
problem with multiple algorithms, which is fine. So you
yeah,
have covered quite a few algos. Okay. Okay, that's fine. Continue, please.
yes, sir. So now we can also predict the heart disease by using neural networks. So this is the simplest code of an ANN. So here we are using uh, ReLU as an activation function. ReLU is nothing but the rectifier linear unit. This allows one to eliminate negative units in an ANN. And then we are using a sigmoid, which is also an activation function. When we are interested in probability mapping, like classification, to be precise, like zeros, like binary classification, then it is appropriate to use sigmoid as our activation function. And then and then we're going to use binary cross entropy loss, which is also called as sigmoid cross entropy. It is a very good loss function which minimizes the loss between two probability distributions, that is the predicted and the actual one. And then we are using Adam, which is an optimizer. It is known to provide best performance, so we normally use Adam. And then metrics is equal to accuracy is used to determine the accuracy. But we have used just 300 epochs over here. So since we have used just 300 epochs over here, and our neural network over here is not quite complex, we can see that we're going to get less accuracy, which is of about 78.69%. Now I'm going to show you another code wherein I have used of about 2000 epochs. So the same procedure. First, I'm gonna import all these libraries, and then the data set, and then this is the code. Wherein here you can see that I've used batch normalization. This addresses the vanishing or exploding gradients problems. And then I've used even dropout. Dropout is the most popular method for regularization, where it drops out uh, some of the some of the values uh, some of the values randomly, which increases the regularization. Again, here down we can see again we have used activation as ReLU, rectified linear unit. And then again, the second layer we have used batch normalization, and then dropout, and then the activation here we have used as sigmoid, so that it can properly predict whether the person has heart disease or not. And then similarly, the loss over here we've used is binary cross entropy, then the optimizer Adam, then matrix is equal to accuracy to show the accuracy value. So now we can here see that it is 80.33%. So finally, to conclude, we can say that now you can observe when we used logistic regression classifier, we saw this much about 82 to 83% to be the accuracy, and naive Bayes, then SVM, then k nearest neighbors, decision tree, random forest, XT boost, and neural networks to give an accuracy of this much. But we actually observed that random forest gave us the highest accuracy rate. I can just scroll back and I can show you the exact accuracy rate, which is 95.08%. So we are going to conclude saying you that random forest classifier is the most appropriate classifier to be used to predict heart disease in a person. These are just the basic optimizers and the regularizations which we use in the code, which just now I just briefed you about, and I just explained you about the final output as well. And now so far we have seen the risk factors that are affecting and that are causing the heart disease. Now I think it is our turn to take precautions. The best precautions over here is to keep your body fit by exercise or by doing yoga, and then not to take too much stress regarding anything, and to have a peaceful mind, and to have a good amount of sleep, and to quit smoking and alcohol, and then to have a healthy diet with all nutrients, proteins, and all the vitamins. And then you don't actually have to lose your weight, but staying healthy and at the same time keeping check your cholesterol levels will help you to overcome the risk factors which will be causing heart disease. And now, as we know, there's this famous quote saying prevention is better than cure. Hence, I just briefed you about the preventions. Thank you, and see you again in our next webinar. I would like to answer the questions if any are there.
Yeah.
So you bundled some free healthcare advice in the end, huh? Okay, good. So all right. So it was an AI lecture, but ending with the dietetic or lifestyle habits. Fair enough. So good session. So audience, any questions for our BMS student interns here? So they compared a lot of algorithms for the same data set, which is also in interesting paradigm, and compared the accuracy. So a decent job. Audience, any questions? Okay, final call. All right. So in that case, there are no any questions. So I think everything was clear also. So thank you, Mahima and Meghna. Good job. And thank you, audience, for attending. And we'll see you in our future webinars. All right. So thanks once again to Meghna and Mahima for preparing this session. And thank you, audience, for attending. We'll see you in future webinars. Have a good night or good day, as the case may be in your time zone.
Yes.
Thank you, sir.
Thank
Thank
you.
you for
Thank you all.
Again in our